Have you ever stopped to think about how these AI assistants actually work? I mean, how does a machine that's basically just a superpowered text predictor turn into something that can give you helpful advice, write a poem, or debug your code? Well, it's quite a journey, and we're about to walk through exactly how it happens. So that's really the big question, isn't it? How do you take this enormous, kind of chaotic library of all the text on the internet and teach it not just what to say, but how to say it in a way that's actually useful to us? That's what this is all about. We're going to break down its life into three distinct phases. And this just perfectly shows the transformation. You ask a simple question: how do I wash my teddy bear? The base model on the left, it just finishes your sentence, predicting the most likely words, and its advice is terrible. You destroy the teddy bear. But look at the right. The tuned model understands what you actually want. It acts like a helpful assistant, giving you safe, step-by-step instructions. So how do we get from the left to the right? Okay, it all starts here, in phase one. You can think of this as the model's infancy. It's not learning to talk or to help. Not yet. It's just being a knowledge sponge, absorbing, basically the entire world of written information to build this foundation of how language works. This whole stage is called pre-training, and the goal sounds almost ridiculously simple. Just predict the next word. That's it. The model gets fed trillions, and I mean trillions of words from the internet, from books, from code, and its only job is to guess what comes next. But don't let that simplicity fool you. This is, by far, the most expensive and computationally insane part of the entire process. And the scale, it's just hard to even wrap your head around. A model like Llama 3 was trained on 15 times trillion tokens of data. That is not a typo. That's like reading the entire internet, not once, but many, many times over. It's an unbelievable volume of text. And to chew through all that data, you need a completely staggering amount of computation. We're talking on the order of 10 to the 25th power floating point operations. This is the kind of job that takes thousands of top-of-the-line GPUs all running nonstop for months. And of course, all of that compute power comes with an absolutely massive price tag. Hundreds of millions of dollars for a single training run. And this right here is a key insight. This means that building these foundational models from scratch, it's not a garage startup thing. Only a handful of the biggest tech companies on the planet have the resources to even attempt it. Now, what's so cool is that this is only even possible because of some seriously brilliant engineering. You have these techniques like flash attention, which came out of Stanford, that basically reinvent how the model processes information. They get rid of memory bottlenecks and make these giant computations actually feasible on the hardware that we have today. But, this phase isn't perfect. It has some real drawbacks. Besides the crazy cost, the model's knowledge is basically frozen in time. It has a knowledge cutoff date, meaning it knows absolutely nothing about anything that happened after its training data was collected. Plus, there's always the risk it might just spit back, plagiarize, something it saw in its training data. So at the end of this phase, what we have is a machine that knows a lot, but it isn't helpful yet. And that brings us to phase two. This is where the magic happens. This is where the model goes from being a sort of text-predicting parrot to a genuinely helpful assistant. If pre-training was about just absorbing facts, this phase is all about learning the social skill of conversation. The main technique here is called supervised fine-tuning, or SFT for short. Now, instead of feeding it the entire internet, we train the model on a much smaller, really carefully curated data set. And this data set is filled with high-quality examples of prompts and the kind of ideal answers we want the model to give. So this is the really critical point. You see the shift in both the goal and the data. We go from a goal of predict the next word using trillions of tokens of raw internet data over to a goal of follow instructions using just a few thousand or maybe a million perfect human-vetted examples. It's a huge change in approach. So what is it actually learning to do? Well, it's learning the patterns of being helpful, how to properly answer a question, how to write a story when asked, how to generate a list or explain something, or really importantly, how to follow safety rules and refuse harmful requests. It's learning the actual structure of a useful, good response. Exactly. This quote just nails it. The model isn't really learning new facts here. Its knowledge base was already built during that massive pre-training phase. This stage is all about teaching it a persona, the character of a safe, helpful, and cooperative AI assistant that knows how to use the knowledge it already has. All right, so we've built the knowledge base and we've taught it the character. But how do we know if it actually worked? Is it any good? Well, that's phase 3. It's the performance review. This is all about evaluation, grading the model to see if it's actually helpful and reliable. And this brings up a really fascinating modern problem. I mean, if you have an AI that can write a perfect essay, who grades it? You could ask humans to grade millions of AI responses, but that would be incredibly slow and expensive. And if the AI is already better than us at some things, how do we even evaluate it effectively? Well, the solution is a little meta. We use another, even more powerful AI to do the grading. This whole method is called LLM as a judge. It's pretty much what it sounds like. You use a really powerful master model, think something like GPT-4 or Gemini, to act as the grader for the student model that you're testing. And it doesn't just give it a score, it has to explain why it gave that score. And the process is very structured. You give the judge AI the original prompt, you give it the student model's answer, and you give it a clear set of grading rules. Now here's the really interesting part. The judge is specifically told to write out its step-by-step reasoning before it gives the final score. This forces it to kind of think through the problem, and it dramatically improves how good the evaluations are. But this system isn't perfect. These judge AIs, they have their own little quirks and biases. They can have a position bias, where they just kind of prefer the first answer they see. They can have a verbosity bias, where they think longer answers are better answers, even when they're not. And they can have a self-enhancement bias, where they give better scores to answers that sound, well, like something they would have written. So understanding these biases is really important because this whole process, from training to fine-tuning to evaluation, it's a never-ending cycle of improvement. So let's zoom out for a second and put this entire three-phase journey together. This table just sums it all up so nicely. You have pre-training. The goal is to learn language, the data scale is massive, and the key challenge is the cost and the compute. Then you have fine-tuning. The goal is to learn helpfulness, the data is much smaller and curated, and the challenge is getting that high-quality data. And finally, evaluation. The goal is to measure quality, and the real challenge there is being objective and watching out for bias. And that leaves us with one last but really crucial question to think about. As these AI judges get better and better at grading each other, the whole process of improving AI is going to speed up like crazy. But what does that mean for our role? What's the future for human feedback in this loop? That's a thought to take with you.